Hopefully you remember bond polarity. Remember that this has to do with the difference in electronegativity, or the ability of an atom to kind of suck electron density toward itself. But the difference in electronegativity between two bonded atoms. And so if the bonded atoms are the same, like oxygen-oxygen or carbon-carbon, and then the one exception to this is carbon-hydrogen, if they're the same, then you're going to have a really low difference in electronegativity between the two bonded atoms, and that's nonpolar. If you have kind of this middling, middle of the road difference, like if you have two different nonmetals bonded together, like oxygen, hydrogen, carbon, oxygen, nitrogen, hydrogen, then that's a polar covalent bond. And actually in organic chemistry, that's the region of this table that we're most interested in. And then if you have a metal and a nonmetal, then you're going to have an ionic interaction, and that's where you have a very low electronegativity coupled with a very high electronegativity. Actually, I guess it's the other way around. All right, so you know, you might have to sometimes categorize bonds as polar covalent or nonpolar covalent, and if you have, like I said, two elements that are different, then those are going to be polar covalent, and that's what we're going to talk about in organic chemistry. If the elements are the same, it's nonpolar covalent. And then you also have this one exception to that rule, which is carbon-hydrogen bond. So when you've got really big molecules, like for instance, here's a sample of an enzyme, that's that ENZ that you see around here. Just imagine this enormous enzyme with an active site, and the active site is shown in here. And what ends up happening is you have these electronegative elements like nitrogen or oxygen that are forming hydrogen bonds. They have differences of electronegativity. They're polar covalent. So you have kind of partial positive and partial negative parts of your active site. And so what that can do is that can then interact with other molecules using these intermolecular forces. An intermolecular force means that there are forces that are occurring between different molecules, or sometimes within larger molecules, single molecules like enzymes or DNA. But they determine properties like boiling point, melting point, solubility, etc. So one thing to remember about intermolecular forces, IMFs, is that they are always weaker than things like covalent bonds. And so, so dispersion forces, we're going to look at these in just a minute though, the types of intermolecular forces. Dispersion, dipole-dipole, ion-dipole, hydrogen bonding. These are all weaker, although they vary, compared to the covalent bonds that we have within the molecules. In general, the stronger intermolecular force, that means that you have the higher boiling or melting point. And so if we look at our examples here, we can see here with propane, we just have van der Waals forces, London dispersion forces, whatever you want to call them. And then we have dipole-dipole forces for here, that's kind of a fixed dipole with our acetaldehyde, and then ethanol can form hydrogen bonds, and that's a stronger type of intermolecular force. And you can then see that even though these have similar molecular masses, their boiling point goes up by quite a bit, and that shows you that the intermolecular force strength is also going up. Okay, so just kind of think to yourself, this is something you should be able to answer at this point. If we boil or melt something, the intermolecular forces are broken, but not the covalent bonds. And just make sure that you can answer why. And as you do that, I will go over to a simulation here. And so if you've kind of formulated an answer there, remember that the covalent bonds are stronger. So even when we take this ice and we melt it to become water by adding heat, we're only breaking the intermolecular forces. We are not breaking the covalent bonds because it takes more energy to create to break those covalent bonds. So there's two determinants, two things to look for when you're comparing the strength and therefore the relative boiling point of molecules. The weakest one of those characteristics is the type of interaction, and the other is how much surface area or contact there is between the molecules. So the weakest type is the London dispersion forces or van der Waals forces. I don't care which one you call them. And those are temporary. They happen between all molecules. And basically what happens is there'll be like this temporary point in time when you'll just happen to get electrons are kind of moving around all the time. And every once in a while, you'll just get more electron density on one side of the molecule than the other, which gives you a negative charge on one side and positive on the other. And so they'll then induce a dipole in the adjacent molecule and then make those molecules stick together. Slightly stronger is the dipole-dipole interaction is when you have a permanent dipole, and in a permanent dipole you have a partial positive charge, and that's then going to interact with another molecule with a partial negative charge. And then we have hydrogen bonds, and hydrogen bonds are stronger still, and they really are just a type of dipole-dipole interaction. And so you have the partial negative charge and the partial positive charge of the hydrogen on an adjacent molecule, and those are then attracted to one another. Okay, so shape also matters. It has to do with the surface area. And so if your molecule is highly branched and more kind of a ball shape, you'll get less of a good interaction between the surface area. Whereas if you have sort of these long, thin molecules, there's more surface area for interactions, and you'll have stronger intermolecular forces. And finally, intermolecular forces determine solubility. And in general, like polarity dissolves like polarity. So if you have two molecules that are polar, they'll be miscible. If you have two molecules that are not polar, they'll be miscible. If you like spicy food, for instance, you should cook the spicy food in your peppers or what have you in oil, because capsaicin, which is shown down here, is mostly a nonpolar molecule. It does have some polar bits to it, but most of it is nonpolar. It's soluble in nonpolar solvents like oil. And so when you cook, it will actually draw the pepper out into the oil. Some of our vitamins are fat soluble and others are water soluble. So vitamin C, it has lots of those OH groups on there. And so those are a lot like water, it has similar polarity. So vitamin C is water soluble. Here, next week, we'll look at how we're drawing this. Basically, this is just carbons and hydrogens in here. And that's nonpolar overall. And so it's gonna dissolve in nonpolar solvents. And one of our most important examples of polarity is the cell membrane. Cell membranes have both a polar and a nonpolar part, and that makes them self-assemble in the body, where you have the nonpolar parts interacting with each other, the polar parts on the outside, to give you the lipid bilayer.